Right now, as you settle into this moment, sunlight that began its journey 8 minutes ago is arriving at Earth. Not 8 minutes from when the sun created it, but 8 minutes of crossing the empty space between our star and this world. That light left the sun's surface traveling at 186,000 miles per second, moving through the void in a straight line, carrying warmth and energy across 93 million miles of solar system. By the time it reaches the upper atmosphere, it has traveled farther than most things in human experience ever will. And yet, this is something that happens continuously, every moment, without pause. The sun does not hurry. It does not need to. For 4.5 billion years, it has maintained a rhythm so steady that life on Earth has organized itself around its constancy. This is not a story about violence or chaos, though the sun is capable of both. This is a story about persistence, about processes so reliable they become invisible, about a sphere of plasma 109 times wider than Earth that has kept a careful balance between gravity and pressure for longer than continents have existed. We're going to spend some time together exploring the sun, but not as something to fear or marvel at with anxiety. Instead, we'll move slowly through its layers, through its cycles, through the quiet mathematics of its existence. There will be numbers, some of them very large, but they won't be overwhelming. They're simply measurements of distance, of time, of energy, offered without urgency. You can listen to this while you rest, while you work, while you simply exist in your own time. The sun itself makes no demands of you. It will be there tomorrow, doing exactly what it has done for billions of years. There is something deeply calming in that kind of reliability. So let's begin at the beginning. Or at least, at a beginning. Let's start with what the sun is, where it sits in space, and why its very ordinariness makes it so perfectly suited to support a planet where beings can pause and wonder about stars. The sun is a star. This feels worth stating plainly because sometimes we forget that the bright disk we see in the daytime sky is the same kind of object as the distant points of light we see at night. It is a star, specifically a G-type main sequence star, sometimes called a yellow dwarf, though it is neither particularly yellow nor particularly dwarf-like. These classifications are relative to other stars, and in the immense variety of stellar objects in the galaxy, the sun finds itself comfortably in the middle range of size, temperature, and luminosity. Its diameter is approximately 864,000 miles, or if we prefer metric units, about 1.39 million kilometers. This is a distance so large that if you could drive a car at highway speeds, 60 miles per hour, without stopping, it would take you about 600 days, or nearly 2 years, just to travel from one side of the sun to the other. Of course, you cannot drive across the sun. There is no surface to drive on. But the comparison helps put the scale in perspective. To give that dimension some sense of scale in relation to our own planet, you could line up 109 Earths side by side across the sun's equator. Imagine standing on Earth and looking up at the sky, trying to picture 109 versions of the entire planet. All the continents, all the oceans, all the mountains and valleys lined up edge to edge. That is how wide the sun is compared to Earth. It is a difference of scale that is difficult to truly internalize because we have no everyday experience with objects this large. The comparison becomes even more striking when we consider volume rather than diameter. Volume scales with the cube of the radius, so small differences in size translate into large differences in volume. If the sun were hollow, which it is not, but if we imagine it as an empty shell, you could fit about 1,300,000 Earths inside it, assuming the Earths were squishy and could pack together without gaps. That is 1.3 million Earths. If you started filling the hollow sun with Earths at a rate of 1 per second, it would take you about 15 days to fill it completely. This is not meant to diminish Earth or make you feel small. Earth is, in its own right, a substantial planet with a diameter of nearly 8,000 miles and a mass of 6 times 10 to the 24th kilograms. It is the largest of the rocky planets in the solar system and the 5th largest planet overall. But compared to the Sun, Earth is tiny. This size difference is common in planetary systems. Stars are always vastly larger than the planets that orbit them. It is simply the nature of how gravity works at these scales. The Sun's radius, from its center to its visible surface, is about 432,000 miles, or 696,000 kilometers. This distance is larger than the distance from Earth to the Moon, which is about 238,000 miles. If you could place the Sun where Earth is, its surface would extend more than halfway to the Moon's orbit. Alternately, if you place the Sun at the location of the Moon, its surface would stretch well past Earth, engulfing our planet entirely. Comparisons to familiar distances help, but they can only go so far in making the Sun's size comprehensible. Perhaps a better way to think about it is in terms of journeys. Light travels at 186,000 miles per second, the fastest speed possible in the universe. At this speed, light can circle Earth's equator 7.5 times in 1 second. Yet it takes light about 2.3 seconds to travel from the center of the Sun to its surface. The Sun is so large that even light, traveling at the ultimate speed limit, takes multiple seconds to cross it. Or consider this. If you could somehow walk across the Sun's diameter at a steady pace of 3 miles per hour, the journey would take you about 33 years. An entire human lifetime spent walking continuously would not be enough to cross the Sun even once. This is the scale we are talking about. It is vast, not in the sense of being infinite or incomprehensible, but in the sense of being much, much larger than anything in our daily experience. The Sun is not the largest object in the solar system by a small margin. It is overwhelmingly the largest. Jupiter, the largest planet, has a diameter of about 87,000 miles, which makes it about 1/10 the diameter of the Sun. If you tried to line up Jupiters across the Sun's diameter, you could fit about 10 of them. And Jupiter itself is enormous, large enough to fit all the other planets inside it. Saturn, the second largest planet, is slightly smaller than Jupiter, with a diameter of about 72,000 miles. Uranus and Neptune are both around 30,000 miles in diameter. Earth, as we have noted, is about 8,000 miles in diameter. Even adding up all the planets, moons, asteroids, and comets in the solar system, the total volume would be dwarfed by the Sun. This is not an unusual situation. In most planetary systems, the central star contains the vast majority of the mass and volume. Planets are minor objects, gravitationally bound to the star, but insignificant in terms of total mass. This is why we call them planetary systems, not co-equal systems. The star is the primary object, and everything else is secondary. The shape of the Sun is very close to a perfect sphere. The difference between the Sun's equatorial diameter and its polar diameter is only about 6 miles out of a total diameter of 864,000 miles. This is a difference of less than 1/100th of 1%. For all practical purposes, the Sun is spherical. This near-perfect sphericity is a consequence of the Sun's gravity. Gravity pulls equally in all directions toward the center, so the Sun naturally takes on a spherical shape. Any deviation from sphericity would create an imbalance in gravitational forces that would quickly be corrected by the movement of plasma. The Sun does rotate, as we have discussed, and this rotation causes a very slight bulge at the equator, similar to the equatorial bulge on Earth. But the effect is tiny because the Sun rotates relatively slowly. A point on the Sun's equator takes about 25 days to complete one rotation, which is much slower than Earth's 24-hour rotation period. The slower the rotation, the smaller the equatorial bulge. For a rapidly rotating object, the equatorial bulge can be quite pronounced. For the Sun, it is almost negligible. When we look at the Sun from Earth, we see a disk. This is because the Sun is so far away that we cannot perceive its curvature directly. The entire Sun subtends. An angle of about half a degree in the sky, which means that if you held up your thumb at arm's length, your thumb would roughly cover the Sun. This small angular size is deceptive because it makes the Sun appear relatively small, even though it is in fact enormous. The apparent smallness is purely a function of distance. If you could move closer to the Sun, it would appear larger and larger until at some point it would fill your entire field of view. Astronauts on the International Space Station, which orbits only a few hundred miles above Earth's surface, see the Sun from essentially the same distance as we do on the ground. The change in distance is negligible compared to the 93 million miles from Earth to the Sun, but spacecraft that have traveled closer to the Sun have sent back images showing a much larger solar disk. The Parker Solar Probe, which has approached to within a few million miles of the Sun, sees a solar disk that fills much more of the sky, appearing many times larger than it does from Earth. These comparisons, these numbers, these descriptions of size and scale, they can only do so much. The Sun is simply very large, larger than anything most of us will ever see in person, larger than any structure humans have ever built, larger than any mountain, any ocean, any continent. It is a sphere of plasma held together by its own gravity, stable and unchanging for billions of years. And it sits at the center of the solar system, binding everything to it with the invisible force of gravity, providing the light and heat that makes life on Earth possible. The Sun's mass is even more impressive relative to Earth. It contains 333,000 times more matter than our planet. Another way to express this is that the Sun accounts for 99.86% of all the mass in the entire solar system. All the planets combined, Jupiter, Saturn, Uranus, Neptune, Earth, Venus, Mars, and Mercury, along with all the moons, all the asteroids, all the comets, all the dust, everything that orbits the Sun together makes up less than 1/5 of 1% of the solar system's total mass. To put this in perspective, imagine a room containing 1,000 objects. 999 of those objects represent the Sun, and the remaining one object represents everything else, all the planets and moons and small bodies. The Sun is not just the center of the solar system by position, it is the solar system, gravitationally speaking, with everything else being relatively minor footnotes orbiting around it. The planets, despite their size and complexity, are essentially debris left over from the Sun's formation, minor perturbations in the Sun's gravitational field. This extreme mass dominance is what gives the Sun such powerful gravitational control over the entire solar system. Every planet, every asteroid, every comet feels the Sun's gravitational pull and is held in orbit by it. Even distant objects in the Oort cloud, hypothesized to be perhaps 1 light-year from the Sun, are still gravitationally bound to it, moving in extremely long orbits that take millions of years to complete. Yet despite this enormous mass, The Sun is not particularly dense compared to Earth. The average density of the Sun is about 1.4 times the density of water. A cubic centimeter of solar material would weigh about 1.4 grams if you could somehow scoop it out and place it on a scale at room temperature. Though, of course, in reality, the material would immediately expand and disperse, because it is plasma held together only by the Sun's gravity. Earth, by contrast, is about 5.5 times denser than water. A cubic centimeter of Earth, if you average together all the rock and metal from the surface to the core, would weigh about 5.5 grams. This means Earth is denser than the Sun by a factor of nearly 4. This seems counterintuitive given that the Sun is so much more massive. But the Sun is made almost entirely of hydrogen and helium, the lightest elements, while Earth is made of heavier elements like iron, oxygen, silicon, and magnesium. This is because the Sun is not made of rock and metal like Earth. It is made almost entirely of hydrogen and helium in a state of matter called plasma. At the Sun's surface, about 91% of atoms are hydrogen and about 8.9% are helium. Everything else, all the heavier elements like oxygen, carbon, iron, and so on, makes up less than 0.1% of the Sun's composition. The Sun sits at a distance from Earth of approximately 93 million miles. This distance is so commonly referenced in astronomy that it has its own unit of measurement called the astronomical unit, or astronomical unit. 1 astronomical unit equals 93 million miles, or more precisely, about 149.6 million kilometers. This is the average distance because Earth's orbit is not a perfect circle. At its closest approach, called perihelion, Earth comes within about 91.4 million miles of the Sun. At its farthest point, called aphelion, the distance stretches to about 94.5 million miles. But for most purposes, we use the average figure of 93 million miles. At this distance, traveling at the speed of light, it takes photons about 8 minutes and 20 seconds to cross the space between the Sun's surface and Earth's atmosphere. This means that when you look at the Sun, you are not seeing it as it is right now. You are seeing it as it was slightly more than 8 minutes ago. The Sun could theoretically cease to exist at this very moment, and we would not know for 8 minutes and 20 seconds. Of course, the Sun is not going to cease to exist. It is far too massive and stable for that. But the 8-minute light delay is a small reminder that even our closest star is separated from us by a vast distance. This distance is not arbitrary. It is, in a very real sense, exactly the right distance for Earth to support life as we know it. Closer, and the planet would be too hot, with water boiling away into space. Farther, and it would be too cold, with water permanently frozen. The region around a star where liquid water can exist on a planet's surface is called the habitable zone, and Earth sits comfortably within the Sun's habitable zone. Not at the inner edge, where things get precarious, and not at the outer edge, where cold begins to dominate. Somewhere in the middle, where conditions have remained stable enough for life to emerge and persist for billions of years. The Sun is not stationary in space. It orbits the center of the Milky Way galaxy at a speed of about 500,000 miles per hour. At this velocity, it takes approximately 225 to 250 million years for the Sun to complete one orbit around the galactic center. This period is sometimes called a galactic year. In the 4.6 billion years since the Sun formed, it has completed about 20 to 25 orbits around the galaxy. Each time it completes an orbit, it passes through different regions of the galaxy, moving through spiral arms and quieter zones between them. As the Sun moves through the galaxy, it takes the entire solar system with it. Earth, Mars, Jupiter, all the planets, along with countless smaller bodies, are bound to the Sun by gravity and travel with it on this long journey through space. The motion is smooth and continuous. We do not feel it because we are moving with the Sun, carried along in its gravitational embrace. The Sun formed about 4.6 billion years ago from a collapsing cloud of gas and dust called a molecular cloud. Most of the mass in that cloud fell toward the center, heating up as gravity compressed it. When the core became hot enough and dense enough, nuclear fusion ignited, and the Sun began its life as a star. The leftover material from that cloud formed a rotating disk around the young Sun, and within that disk, over millions of years, planets began to coalesce from smaller particles sticking together. This process was not instantaneous. The Sun took about 50 million years to collapse from a cloud to a star. During that time, it was a protostar, not yet hot enough in its core for fusion to begin. Once fusion started, the Sun entered what is called the main sequence phase of its life, which is the long, stable period when a star fuses hydrogen into helium in its core. The Sun has been in this phase for the past 4.6 billion years, and it will remain in this phase for another 5 billion years or so. More than half its life as a main sequence star is still ahead. The Sun's temperature varies dramatically depending on which layer you measure. At the surface, in the layer called the photosphere, the temperature is about 10,000 degrees Fahrenheit, or about 5,500 degrees Celsius. This might sound extremely hot, and it is by terrestrial standards, but it is cool compared to what happens deeper inside. As you move inward through the Sun's layers, the temperature rises. At the very center, in the core, temperatures reach about 27 million degrees Fahrenheit, or 15 million degrees Celsius. These temperatures are not violent or chaotic in the way we might imagine. They are simply the natural consequence of gravity compressing matter to immense densities. The core is extraordinarily dense, about 150 grams per cubic centimeter, which is about 150 times denser than water and approximately 8 times denser than gold. This density, combined with the high temperature, creates the conditions necessary for nuclear fusion to occur. The Sun will not always be as it is now. In about 5 billion years, it will begin to run out of hydrogen in its core. When that happens, the core will contract, heating up further, and the outer layers will expand. The Sun will become what is called a red giant. During this phase, it will grow large enough to engulf the inner planets, possibly including Earth. But this is so far in the future that it exists outside the scope of anything we need to consider in human terms. 5 billion years is longer than the Earth has existed. It is longer than complex life has existed. It is time on a scale so vast that it becomes abstract. For now, and for countless generations to come, the Sun will remain stable, constant, and predictable. It will rise and set. It will provide light and warmth. It will continue the processes that have sustained it for billions of years. This is what the Sun does. This is what it has always done. And there is a certain quiet comfort in that knowledge. Let's move deeper now, down through layers of plasma to the place where the Sun's energy originates. The core is not a distinct physical boundary, but rather a region defined by temperature and density extending from the Sun's center to about 20 to 25% of its radius. This means the core occupies a relatively small volume compared to the Sun as a whole, yet it contains about 34% of the Sun's total mass. Everything is compressed here, squeezed by the immense weight of the layers above. In this core, hydrogen nuclei, which are simply protons, are moving at tremendous speeds because of the high temperature. Temperature, after all, is just a measure of how fast particles are moving. At 15 million degrees Celsius, protons are moving so quickly that when they collide, they occasionally overcome the electromagnetic force that normally pushes positively charged particles apart. If two protons can get close enough, the strong nuclear force takes over and they can fuse together. The electromagnetic force is what keeps protons apart under normal circumstances. Protons are positively charged and, like charges, repel. In everyday matter at room temperature, protons are safely locked inside atomic nuclei, surrounded by clouds of electrons that keep them separated from the protons in other atoms. But in the sun's core, there are no atoms in the conventional sense. The temperature is so high that electrons have been stripped away from nuclei, creating a plasma where protons and electrons move freely. Even in this plasma state, the electromagnetic repulsion between protons is extremely strong. To overcome this repulsion, two protons must approach to within about 1 femtometer of each other, which is 1 quadrillionth of a meter. At this distance, the strong nuclear force, which is much more powerful than the electromagnetic force but only works at very short ranges, can bind the protons together. Getting two protons this close requires them to be moving at very high speeds, which is why fusion only occurs at such extreme temperatures. The probability of any single collision between two protons resulting in fusion is extremely low. Most collisions simply result in the protons bouncing off each other. The energy barrier to fusion is high, and quantum mechanics tells us that particles must tunnel through this barrier for fusion to occur. Quantum tunneling is a phenomenon where particles can pass through energy barriers that they classically should not be able to cross. Even with tunneling, the probability is small. On average, a proton in the sun's core will wander around for about 9 billion years before successfully fusing with another proton. 9 billion years is longer than the current age of the sun. This means that, on average, most protons in the core have not yet undergone fusion. They are still waiting for their turn. This extraordinarily long waiting time is part of why the sun can last so long. The fusion rate is slow enough that the sun's fuel supply will last for billions of years. Even though fusion is happening continuously, this is not a simple process. When two protons do successfully fuse, the result is unstable. Two protons cannot form a stable nucleus on their own because there is no stable isotope of helium with two protons and no neutrons. Instead, almost immediately after the fusion, one of the protons undergoes beta plus decay. In this decay process, mediated by the weak nuclear force, the proton transforms into a neutron, a positron, which is the antimatter counterpart of an electron, and a neutrino. The positron almost immediately encounters an electron in the surrounding plasma and annihilates, producing two gamma-ray photons. The neutrino escapes from the sun entirely, carrying away a small amount of energy. The result of this first step is a nucleus containing one proton and one neutron, which is called deuterium or heavy hydrogen. Deuterium is stable. It can exist indefinitely without decaying. In the dense, hot core of the sun, this deuterium nucleus will soon encounter another proton. When they collide with sufficient energy, they can fuse to form helium-3, a nucleus with two protons and one neutron. This reaction releases another gamma-ray photon. Helium-3 is also stable, but it is not the end of the chain. Two helium-3 nuclei can collide and fuse to form helium-4, which has two protons and two neutrons, releasing two protons back into the plasma. Helium-4 is the most common isotope of helium in the universe and is extremely stable. It is the final product of this fusion chain, known as the proton-proton chain or PP chain. The net result of all these steps is that 4 hydrogen nuclei have been converted into one helium nucleus, with a small amount of mass converted into energy according to Einstein's equation E equals mc squared. The mass difference is tiny, only about 0.7% of the original mass of the 4 hydrogen nuclei. A helium-4 nucleus weighs slightly less than the 4 protons that went into making it. The missing mass has been converted into energy. Because the speed of light is such an enormously large number, approximately 300 million meters per second, and because this number is squared in Einstein's equation, even a tiny amount of mass converts into a substantial amount of energy. Specifically, when 4 protons fuse to form one helium nucleus, about 26.7 million electron volts of energy is released. In more familiar units, this is about 4.3 times 10 to the minus 12th joules. This might not sound like much, but remember that this is happening trillions upon trillions upon trillions of times every second throughout the core. The energy released in each fusion reaction is initially in the form of gamma-ray photons and the kinetic energy of the particles involved. These gamma rays are the highest energy form of electromagnetic radiation, with wavelengths shorter than the size of an atomic nucleus. They carry a tremendous amount of energy in each photon, far more than visible light photons. In addition to the energy from the gamma rays, there is also the energy carried away by neutrinos. Neutrinos are strange particles. They have almost no mass, travel at nearly the speed of light, and interact extremely weakly with ordinary matter. A neutrino can pass through the entire sun without being absorbed or deflected. In fact, neutrinos can pass through light years of solid lead without interacting. Because they interact so weakly, neutrinos produced in the core escape from the sun almost immediately, taking their energy with them. About 2% of the energy produced by fusion escapes in the form of neutrinos, never contributing to the sun's heat or light. The remaining 98% of the energy, carried by gamma-ray photons and the motion of particles, stays in the sun and gradually works its way outward. This is the energy that eventually reaches Earth as sunlight. The journey of this energy from the core to the surface is what we explored earlier, the random walk, through the radiative zone that takes 170,000 years on average. There is an alternative fusion process that can occur in stars called the carbon-nitrogen-oxygen cycle, or CNO cycle. In this process, carbon, nitrogen, and oxygen nuclei act as catalysts, facilitating the fusion of hydrogen into helium. The CNO cycle produces the same result as the proton-proton chain, converting 4 protons into one helium nucleus, but it does so through a different series of reactions. The CNO cycle is more sensitive to temperature than the proton-proton chain and dominates in stars that are hotter and more massive than the Sun. In the Sun, the CNO cycle contributes only about 1% of the total energy production. The vast majority comes from the proton-proton chain. But as the Sun ages and its core becomes hotter, the contribution from the CNO cycle will gradually increase. By the time the Sun is nearing the end of its main sequence life, the CNO cycle might contribute a few percent of the energy, though the proton-proton chain will still be dominant. The proton-proton chain is a 3-step process, as we have described, but there are actually several variations and branches in the reaction pathway. The most common branch is called PP1, which is the sequence we have described. There are also less common branches called PP2 and PP3, which involve the creation and destruction of heavier isotopes like beryllium and lithium. These branches become more important at higher temperatures, but contribute only a small fraction of the total energy in the Sun. The conditions required for the proton-proton chain to operate are extremely specific. The temperature must be at least a few million degrees, and the density must be high enough that collisions between protons occur frequently. Below a certain temperature, fusion does not occur at all, no matter how dense the material is, because protons simply do not have enough kinetic energy to overcome the electromagnetic repulsion, even with quantum tunneling. This is why planets, even massive ones like Jupiter, do not undergo fusion. Jupiter is about 300 times more massive than Earth and is composed mostly of hydrogen, the same fuel the Sun uses. But Jupiter is not massive enough for its core to be compressed to the temperatures and densities required for fusion. Jupiter's core is hot, perhaps 20,000 degrees, but this is nowhere near the 15 million degrees needed for fusion. Jupiter is essentially a failed star, or more accurately, a planet that never had any possibility of becoming a star because it is far too small. To ignite hydrogen fusion, an object needs to have a mass of at least about 75 times the mass of Jupiter, or about 0.075 times the mass of the Sun. Objects below this mass threshold are called brown dwarfs. They are too massive to be planets, but not massive enough to be stars. Brown dwarfs can fuse deuterium, which requires lower temperatures than hydrogen fusion, but they cannot sustain hydrogen fusion. Without hydrogen fusion, they gradually cool and fade over time. The Sun is comfortably above the mass threshold for hydrogen fusion. It has been fusing hydrogen in its core for 4.6 billion years and will continue to do so for another 5 billion years. The core contains enough hydrogen to sustain fusion for this entire period. As fusion proceeds, the core gradually becomes enriched in helium at the expense of hydrogen, but there is so much hydrogen to begin with that the process can continue for an extraordinarily long time. The rate of fusion in the core is controlled by the temperature and density. If the rate were to increase, producing more energy, the additional heat would cause the core to expand slightly. This expansion would reduce the density and temperature, slowing the fusion rate back down. Conversely, if the rate were to decrease, the core would contract slightly. Under gravity, increasing the density and temperature, and speeding up the fusion rate. This negative feedback loop keeps the Sun stable. It is a self-regulating system, maintaining a balance between gravity, trying to compress the core, and pressure from fusion, trying to expand it. This balance, called hydrostatic equilibrium, is what allows the Sun to remain stable for billions of years without collapsing or exploding. It is a delicate balance, but it is also robust. Small perturbations are automatically corrected by the feedback mechanisms built into the Sun's structure. The Sun does not need to be carefully managed or controlled. It simply follows the laws of physics, and those laws naturally lead to stability. Every second, the Sun's core converts about 600 billion kilograms of hydrogen into helium. Of that mass, about 4 billion kilograms are converted directly into energy, which is then radiated outward. This is the source of the Sun's power. This is what makes it shine. 4 billion kilograms every second sounds like an almost incomprehensible rate of consumption, but the Sun is so massive that it can sustain this rate of fusion for billions of years without exhausting its fuel supply. The total energy output of the Sun, measured in watts, is about 3.846 times 10 to the 26th power. That is 384.6 followed by 24 zeros. To give this some perspective, if you could capture all the energy the Sun produces in one single second and use it to power a typical household, you would have enough energy to keep that household running for about 100 trillion years. The sun produces this much energy continuously, second after second, year after year, for billions of years. Interestingly, the sun's core does not produce energy as intensely as you might think on a per-volume basis. The power density in the core, which is the amount of energy generated per cubic meter, is only about 276.5 watts per cubic meter. For comparison, the human body, through its metabolism, produces a power density of around 1000 watts per cubic meter. An active compost heap produces even more. The sun's core, per unit volume, is actually less energetic than a compost pile. So why is the sun so bright? The answer is simply that it is enormous. The core may not be intensely powerful per cubic meter, but there are an almost incomprehensible number of cubic meters in the core, all producing energy simultaneously. The sun's total power output is huge, not because it is extraordinarily efficient at any given point, but because there is so much of it. This is actually reassuring in a way. The sun is not some barely controlled explosion waiting to run away into chaos. It is a massive, stable system where fusion happens at a relatively gentle rate across an enormous volume. The balance between gravity, trying to compress the core, and the outward pressure from fusion energy, trying to expand it, has been maintained for billions of years. This balance is called hydrostatic equilibrium, and it is what keeps the sun stable. If fusion in the core were to increase for some reason, producing more energy, that would create more outward pressure, causing the core to expand slightly. As the core expands, it cools, and the fusion rate decreases back to normal. Conversely, if fusion were to decrease, the core would contract slightly under gravity, heating up, and the fusion rate would increase back to normal. The sun self-regulates. It has built-in feedback mechanisms that keep it stable. The helium created by fusion does not rise to the surface. It is denser than hydrogen, so it tends to sink and accumulate in the core. Over time, the core is slowly enriched in helium at the expense of hydrogen. This is a very gradual process. After 4.6 billion years, the core has gone from being about 70% hydrogen to about 33% hydrogen by mass. The rest is helium. Eventually, billions of years from now, the core will be almost entirely helium, and hydrogen fusion will cease in the core, though it will continue in a shell around the core. But that is a different phase of the sun's life, one that is still very far away. For now, fusion continues steadily in the core. Protons collide, fuse, release energy. That energy begins its journey outward. And here is where things become particularly interesting, because the energy created in the core does not simply travel to the surface and escape into space. The journey from the core to the surface takes a very long time. Not 8 minutes, like the journey from the surface to Earth. Much, much longer. When fusion occurs in the core, it releases energy in the form of high-energy photons called gamma rays. These gamma rays begin moving outward from the point where they were created. But the sun's interior is not empty space. It is dense plasma, packed with protons, helium nuclei, and electrons. The density is so high that the particles are essentially touching each other, with almost no empty space between them. A gamma-ray photon cannot travel far before it collides with one of these particles. When a photon collides with a particle, several things can happen. The most common is that the photon is absorbed by the particle, transferring all its energy to that particle. The particle, now in an excited state with extra energy, cannot hold on to this energy for long. Within a tiny fraction of a second, it must release the energy. It does so by emitting another photon. This new photon is traveling in a random direction. It might be heading roughly outward from the core. It might be heading sideways, perpendicular to the radial direction. It might even be heading back toward the core, undoing the previous photon's outward progress. The direction is determined by quantum mechanical processes and is essentially random. There is no memory, no preferred direction, no bias toward the surface. The photon that is re-emitted may not have the same energy as the photon that was absorbed. Often, the particle will emit a photon with slightly less energy than it absorbed, with the remaining energy converted into kinetic energy, meaning the particle is moving slightly faster. This process, repeated countless times, gradually degrades the energy of photons from gamma rays to X-rays to ultraviolet to visible light to infrared. By the time a photon escapes from the sun's surface, it has lost a significant amount of its original energy through these countless interactions. But let us return to the journey itself. The average distance a photon travels before colliding with something depends on the density of the medium. In the core, where the density is about 150 grams per cubic centimeter, the mean free path, which is the average distance between collisions, is extraordinarily small. Physicists have calculated this to be about 1 millimeter, or in some models, even less. 1 millimeter is about the thickness of a dime. That is how far a photon travels, on average, before being absorbed and re-emitted. Now, the radius of the Sun is about 700,000 kilometers, which is 700 billion millimeters. If a photon could travel in a straight line at the speed of light, covering 300 million meters per second, it would escape the Sun in about 2.3 seconds. But the photon does not travel in a straight line. It follows a random walk, and the mathematics of random walks tells us something remarkable and counterintuitive about how long this journey takes. In a random walk, the net distance traveled after a certain number of steps is proportional to the square root of the number of steps. If you take 100 random steps, each 1 meter long, you might end up only 10 meters away from where you started, because some steps canceled out others, taking you back toward your starting point. To travel a distance d in a random walk with step size L, you need approximately d squared divided by L squared steps. For the photon in the Sun, the distance d is the radius of the Sun, about 700 billion millimeters. The step size L is about 1 millimeter. So the number of steps required is approximately 700 billion squared, which is about 5 times 10 to the 23rd, or 500,000 billion steps. Each step takes about 3 picoseconds, which is 3 trillionths of a second, the time it takes light to travel 1 millimeter. Multiply 5 times 10 to the 23rd steps by 3 times 10 to the minus 12 seconds per step, and you get about 1.5 times 10 to the 12 seconds, or about 48,000 years. But this calculation is simplified. It assumes the Sun has uniform density, which it does not. The density is highest in the core and decreases as you move outward. Near the core, the mean free path is very short and photons make slow progress. Near the surface, the mean free path is much longer and photons can move more freely. When you account for the actual density profile of the Sun, the average time increases. More refined calculations, taking into account the varying density, temperature, and other factors, yield estimates of the photon travel time ranging from about 10,000 years to 200,000 years, with 170,000 years being a commonly cited figure. This is not a small uncertainty. The difference between 10,000 and 200,000 years is significant, but on the timescale of the Sun's age, which is 4.6 billion years, even this range is relatively small. Whether the average photon takes 10,000 years or 200,000 years to escape, the point is that it takes a very long time compared to the 2 seconds it would take in a straight line and a very short time compared to the sun's total age. Let us think about what this means. The sunlight that reaches Earth today, the photons striking your skin if you are standing outside, began their journeys in the sun's core during the last ice age, roughly 170,000 years ago. At that time, modern humans, Homo sapiens, had recently emerged in Africa and were just beginning to spread to other continents. Neanderthals still lived in Europe and Asia. The climate was colder, ice sheets covered much of the northern hemisphere, and sea levels were lower because so much water was locked up in glaciers. Those photons, created in an instant of fusion, have been bouncing through the sun's interior ever since. They have no awareness, no experience of time. They simply exist, moving from interaction to interaction, slowly diffusing outward. While they were making their journey, human history unfolded on Earth. Entire civilizations rose and fell. Art, language, agriculture, cities, writing, all of these developed. While those photons were still trapped inside the sun, bouncing around, gradually working their way toward the surface. Then, finally, after 170,000 years, they reach the photosphere, the visible surface of the sun. There, the density drops suddenly and photons can escape into space. They travel outward in straight lines now, crossing 93 million miles in 8 minutes, arriving at Earth. Some are absorbed by the atmosphere, some by the oceans, some by the land. And some reach a person standing outside, warming their skin, providing the light by which they see the world. This journey from core to surface to Earth is happening continuously. At every moment, new photons are being created in the core, beginning their long random walk. At every moment, photons are escaping from the surface, having completed their journey. The sun is a kind of photon processing machine, taking high-energy gamma rays produced by fusion and converting them, through countless interactions, into the visible and infrared light that we see and feel. The concept of a random walk is not unique to photons in the sun. It appears in many areas of physics and mathematics. The motion of pollen grains on the surface of water, observed by botanist Robert Brown in the 19th century and explained by Albert Einstein in the 20th century, is a random walk caused by collisions with water molecules. The diffusion of molecules in a gas or liquid is a random walk. The path of a stock price over time, in financial models, is sometimes modeled as a random walk. Even the search patterns of some animals, looking for food in an environment where food is randomly distributed, can approximate a random walk. In all these cases, the same mathematics applies. The net distance traveled is proportional to the square root of the number of steps, and the time required to travel a given distance scales with the square of that distance. This is why it takes so long for photons to escape the sun. It is not that they are moving slowly. They are moving at the speed of light, the fastest possible speed. But they are moving in random directions, and this randomness causes them to take far longer to reach the surface than if they could travel in a straight line. There is something almost philosophical about this. The photons are not trying to escape. They have no goal, no direction, no awareness. They simply exist and interact according to the laws of physics. And yet, through the accumulation of countless random events, they eventually do escape, emerging from the sun to light up the solar system. Order emerges from randomness. Purpose emerges from purposelessness. The sun shines not because photons are trying to reach the surface, but because the laws of physics, operating on vast numbers of particles over vast spans of time, inevitably lead to energy flowing from the hot interior to the cooler surface and then into space. Another interesting aspect of the photon's journey is the question of how we know this happens. We cannot directly observe photons inside the sun. The sun is opaque. We can only see the photosphere, the thin outer layer where photons finally escape. Everything we know about the sun's interior comes from indirect evidence. Mathematical models based on the laws of physics, observations of the sun's surface and its oscillations, measurements of neutrinos escaping from the core, and comparisons with other stars. Neutrinos provide a particularly useful window into the sun's core. Unlike photons, neutrinos interact so weakly with matter that they escape from the core almost immediately, taking only about 2 seconds to reach the surface and then another 8 minutes to reach Earth. By detecting neutrinos from the sun, which has been done since the 1960s using massive underground detectors filled with water or other materials, scientists can confirm that fusion is indeed occurring in the core and measure the rate at which it is happening. The neutrino flux matches the predictions of solar models, giving us confidence that our understanding of the sun's interior is correct. The photon's journey through the sun is a reminder of the vast scales involved in stellar physics. The sun is not a simple object. It is a complex, dynamic system where processes occur on timescales ranging from picoseconds, the time between collisions, to billions of years, the lifetime of the star. Understanding how all these processes work together to create a stable, shining star is one of the great achievements of 20th century astrophysics, built on the work of countless scientists over many decades. Physicists have calculated how long it takes, on average, for a photon created in the core to reach the surface through this random walk process. The answer is approximately 170,000 years. Some photons take longer, some take less time, but the average is around 170 millennia. The light that left the sun's surface 8 minutes ago and is now reaching Earth began its journey in the sun's core about 170,000 years ago. At that time, Earth was in the grip of an ice age, and modern humans were just beginning to spread across the planet. This is not a metaphor or an exaggeration. It is a direct consequence of the sun's density and the nature of how photons interact with matter. Each individual collision and re-emission happens almost instantaneously, but with trillions upon trillions of collisions required for a photon to randomly walk from the center to the surface, the total time adds up to millennia. During this journey, something interesting happens to the photons. When a gamma-ray photon is absorbed and re-emitted, it is not always re-emitted as a gamma ray. Sometimes it is re-emitted as a lower energy photon, perhaps an X-ray. With subsequent collisions, the energy continues to decrease. X-rays become ultraviolet photons become visible light, and visible light becomes infrared. By the time a photon finally escapes from the sun's surface, it is much lower in energy than when it started. This is why the sun glows in visible light and infrared, not in gamma rays. The surface is cooler than the core, and the photons have lost energy through countless interactions over their long journey outward. There is something almost meditative about this process. Energy created in an instant of nuclear fusion, then spending 170,000 years bouncing through the interior of the sun, gradually making its way outward, step by step, collision by collision. No single photon remembers where it came from or where it is going. It simply exists in the present moment, interacting with whatever particle it happens to encounter next. And yet, in aggregate, energy flows outward, the sun shines, and life on Earth continues. Physicists sometimes point out that from the photon's perspective, time does not pass at all. According to Einstein's theory of relativity, for an object traveling at the speed of light, time dilation is infinite. A photon experiences no time. From its point of view, its creation and absorption happen simultaneously, even if 170,000 years pass in our reference frame. The photon does not experience the journey. It does not wait. It simply exists at all points along its path at once, in a sense. This is one of those strange consequences of relativity that reminds us how different the universe can be from our everyday experience. But whether we think of it as 170,000 years or as no time at all, the process continues. The sun's core produces energy. That energy slowly radiates outward through the interior and eventually emerges as light that streams across the solar system. This has been happening for 4.6 billion years. It will continue happening for billions more. And in that continuity, in that reliable, patient process, there is something fundamentally calming. The region where this slow outward journey of photons occurs is called the radiative zone. It extends from the core at about 25% of the sun's radius out to about 70% of the sun's radius. This is a substantial portion of the sun's volume, and throughout this entire region, energy is transported by radiation. Photons are absorbed and re-emitted, bouncing from particle to particle, making their slow, random walk toward the surface. The radiative zone is stable. There is no large-scale motion of material here, no churning or mixing. The plasma simply sits in place, held by the balance between gravity pulling inward and pressure pushing outward. Temperature decreases gradually as you move outward through the radiative zone, from about 15 million degrees at the inner boundary down to about 2 million degrees at the outer boundary. The density also decreases from about 150 grams per cubic centimeter at the inner edge to about 0.2 grams per cubic centimeter at the outer edge. Beyond the radiative zone lies the convection zone, which extends from about 70% of the sun's radius out to the surface. In this region, energy is transported by convection rather than radiation. Convection is the process where hot material rises, cools, and sinks back down, creating a cycle of motion. You have probably seen convection in a pot of boiling water or in the atmosphere when warm air rises and cool air sinks. The same process occurs in the sun's convection zone. In the radiative zone, the temperature gradient, which is the rate at which temperature changes with distance, is shallow enough that radiation can efficiently transport energy. But as you move outward, the temperature gradient becomes steeper, meaning temperature drops more quickly with each kilometer of distance. At some point, radiation alone cannot transport energy quickly enough, and convection becomes more efficient. When this happens, hot plasma near the base of the convection zone becomes buoyant and rises. As it rises, it carries energy with it. When it reaches the surface, it radiates that energy into space, cools, becomes denser, and sinks back down. This cycle happens continuously, creating large-scale circulation patterns in the sun's outer layers. The size and duration of these convection cells vary. Some are small, perhaps only a few hundred kilometers across. Others are enormous, spanning tens of thousands of kilometers. The largest convection cells can take weeks or months to complete a full cycle from rising to sinking. These cells are visible on the sun's surface as a pattern called granulation, where bright regions correspond to hot rising plasma and darker regions correspond to cooler sinking plasma. The convection zone is much less dense than the radiative zone. Near the top of the convection zone, just below the surface, the density is about a tenth the density of Earth's atmosphere at sea level. This makes the outer layers of the Sun almost tenuous by comparison to its interior, though still far denser than the near vacuum of space. The surface of the Sun, the layer we actually see when we look at it through a telescope or safely filtered with our eyes, is called the photosphere. The word photosphere means light sphere, and it is called this because this is the layer that emits most of the visible light that reaches us. The photosphere is only about 300 miles thick, which is incredibly thin compared to the Sun's total radius of 432,000 miles. It is essentially a shell of plasma where the density drops rapidly enough that photons can finally escape into space without being immediately absorbed. The temperature of the photosphere is about 10,000 degrees Fahrenheit or 5,700 degrees Kelvin. This is significantly cooler than the layers below, which is why the photons escaping from the photosphere are mostly in the visible and infrared parts of the spectrum. If we could see the layers below the photosphere, they would appear brighter and more blue because they are hotter. But we cannot see those layers directly. They are hidden by the photosphere itself. Above the photosphere lies the Sun's atmosphere, which consists of two main layers, the chromosphere and the corona. The chromosphere is a thin layer, only about a few thousand miles thick, that sits just above the photosphere. Its name comes from the Greek word for color, because during a total solar eclipse, when the bright photosphere is blocked by the moon, the chromosphere becomes visible as a reddish ring around the Sun. This red color comes from hydrogen emission. The chromosphere is hotter than the photosphere, with temperatures rising from about 6,000 degrees at its base to about 20,000 degrees at its outer edge. This is counterintuitive. Normally, we expect temperature to decrease as you move away from a heat source, like when you move your hand away from a fire. But in the Sun's atmosphere, temperature increases as you move away from the surface. This is one of the great mysteries of solar physics, and scientists are still working to understand it fully. Above the chromosphere lies the corona, the Sun's outermost atmospheric layer. The corona extends millions of kilometers into space, gradually thinning out until it merges with the solar wind. The corona is extraordinarily hot, with temperatures reaching between 1 million and 3 million degrees Celsius. This is hotter than the surface of the Sun by a factor of several hundred. How the corona gets so hot is not entirely understood, but it likely involves the Sun's magnetic field depositing energy into the corona through a variety of mechanisms. During a total solar eclipse, the corona is visible as a beautiful, wispy halo around the Sun. Its appearance changes depending on the phase of the solar cycle, with more structure and complexity during periods of high solar activity. The corona is so hot that it glows brightly in X-rays and extreme ultraviolet light, though it is too tenuous to produce much visible light. Special instruments on satellites and telescopes allow scientists to observe the corona in these wavelengths even when there is no eclipse. The transition from the chromosphere to the corona is very sharp, occurring over a region only about 60 miles thick called the transition region. In this narrow boundary, temperature jumps from about 20,000 degrees to about 1 million degrees. The reason for such a rapid temperature increase in such a thin layer is, again, not fully understood and remains an active area of research. The layered structure of the Sun, from core to corona, represents different physical regimes. The core is where fusion happens. The radiative zone is where energy slowly radiates outward. The convection zone is where material churns and mixes. The photosphere is where photons finally escape. The chromosphere and corona are the Sun's atmosphere, dominated by magnetic fields and mysterious heating processes. Each layer plays its role, and together they create the sun we observe. Understanding these layers has taken centuries of careful observation and theoretical work. Early astronomers could only observe the photosphere and, during eclipses, the chromosphere and corona. With the advent of spacecraft and advanced instruments, scientists have been able to probe deeper, using techniques like helioseismology, which studies oscillations and waves on the sun's surface to infer the structure of the interior, much like seismology studies earthquakes to understand Earth's interior. The sun is not uniform or static. It is dynamic, with each layer responding to conditions and processes occurring in the layers around it. But this dynamism occurs within a stable, long-term structure that has persisted for billions of years. The core fuses hydrogen, the radiative zone transports energy outward, the convection zone churns, the photosphere glows, and the corona extends into space. This is the sun's nature. This is how it functions. And in that function, there is order, pattern, and a kind of predictable serenity. From the sun's outermost atmosphere, the corona, particles are constantly streaming away into space. This outflow is called the solar wind, and it extends throughout the entire solar system, creating a vast region of influence known as the heliosphere. The solar wind is not a metaphor. It is an actual wind, composed of particles, mostly electrons and protons, that have escaped the sun's gravitational pull and are traveling outward at high speeds. The word wind might suggest something gentle, like a breeze on a summer day. But the solar wind is nothing like terrestrial wind. On Earth, wind is the movement of air molecules, which have mass and can exert force when they collide with objects. The solar wind is similar in that it consists of particles in motion, but these particles are moving much, much faster than any wind on Earth. The solar wind travels at speeds ranging from about 300 to 800 kilometers per second, which is about 1,000 to 3,000 kilometers per hour. To put this in perspective, a Category 5 hurricane, the strongest classification of hurricane on Earth, has winds that reach perhaps 250 kilometers per hour. The solar wind is thousands of times faster. Despite this tremendous speed, the solar wind is extraordinarily tenuous. At Earth's distance from the Sun, about 93 million miles, the solar wind has a density of only about 5 particles per cubic centimeter. To understand how low this density is, compare it to Earth's atmosphere at sea level, which has a density of about 2.5 times 10 to the 19th particles per cubic centimeter. The solar wind is about 5 quintillion times less dense than sea level air. If you could somehow collect all the solar wind particles in a cube 1 meter on each side, you would have only about 5 million particles, compared to about 25 billion particles in the same volume of air on Earth. This combination of high speed and low density means that the solar wind carries relatively little momentum or kinetic energy per unit volume. A person standing in the solar wind would feel no push, no force, nothing at all. The particles would pass right through, perhaps occasionally colliding with atoms in the person's body, but far too rarely to be noticeable. The solar wind is, for all practical purposes, indistinguishable from a perfect vacuum, except that it has a small number of very fast-moving particles embedded in it. The corona is so hot that particles in it are moving fast enough to reach escape velocity. For the Sun, escape velocity at the distance of the corona, about 1 to 2 solar radii from the center, is several hundred kilometers per second. This is the minimum speed a particle needs to escape the Sun's gravitational pull and never return. Escape velocity decreases with distance, so farther from the Sun, a lower speed is required to escape. But in the corona, where temperatures are in the millions of degrees, particles are moving at hundreds of kilometers per second, which is comparable to or exceeding the escape velocity. Temperature, as we have noted before, is a measure of how fast particles are moving. In the corona, with temperatures of 1 to 3 million degrees Celsius, particles are moving at speeds of several hundred kilometers per second. Not all particles are moving at this speed. In any gas or plasma, there is a distribution of speeds. Some particles are moving slower, some faster. But the average speed is determined by the temperature, and at coronal temperatures, a significant fraction of particles are moving fast enough to escape. When particles escape the Sun, they do not all leave at the same speed. Some are moving just barely fast enough to escape, while others are moving much faster. The particles that escape most easily are those that are moving radially outward, away from the Sun, and are moving faster than the escape velocity. Particles moving tangentially, parallel to the Sun's surface, or moving too slowly, do not escape. They remain bound to the Sun, circulating in the corona. This means that the solar wind is composed of a selected subset of particles from the corona, those that happen to be moving in the right direction at the right speed. The Sun is constantly losing mass through this process, but the amount is minuscule compared to its total mass. The Sun loses about 1 billion kilograms of material per second through the solar wind. This sounds like a lot, but remember that the Sun's total mass is about 2 times 10 to the 30th kilograms, which is 2 followed by 30 zeros. 1 billion is 10 to the 9th. So the ratio is about 1 part in 2 times 10 to the 21st. At this rate, the Sun would need about 60 billion years to lose just 1% of its mass. The Sun's remaining lifetime on the main sequence is about 5 billion years, so the mass loss through the solar wind is completely negligible. It will not significantly affect the Sun's structure or evolution. The solar wind carries the Sun's magnetic field with it into space. This happens because the solar wind consists of charged particles, and charged particles interact with magnetic fields. In a plasma, magnetic field lines are frozen into the plasma, meaning that as the plasma moves, it drags the field lines along with it. This is a consequence of the high electrical conductivity of plasma. The solar wind, streaming outward from the Sun, carries magnetic field lines radially outward into space. But there is a complication. The Sun is rotating, completing one rotation every 25 days at the equator. As the Sun rotates, the base of each magnetic field line is anchored to a specific point on the Sun's surface and is carried around by the rotation. Meanwhile, the outer end of the field line is being carried outward by the solar wind. The result is that the magnetic field lines take on a spiral shape, wrapping around the Sun like the grooves on a vinyl record. This spiral is called the Parker spiral, named after Eugene Parker, the physicist who first predicted its existence. The Parker spiral has practical consequences. Particles accelerated by solar flares or other events on the Sun do not travel radially outward. They follow the spiral magnetic field lines, which means they arrive at Earth from a direction that is not directly along the Sun-Earth line, but at an angle. Understanding the Parker spiral is important for space weather forecasting because it helps predict when particles from a solar event will reach Earth. The magnetic field carried by the solar wind is relatively weak, only a few nanoteslas at Earth's distance. For comparison, Earth's magnetic field at the surface is about 30 to 60 microteslas, which is thousands of times stronger. But the sun's magnetic field, even though it is weak by the time it reaches Earth, has a large-scale structure that extends throughout the solar system, and this structure can interact with the magnetic fields of planets, causing various effects. When the solar wind encounters Earth, it does not strike the planet directly, at least not most of it. Earth has a magnetic field generated by the dynamo action of its liquid outer core. This magnetic field acts as a shield, deflecting most of the solar wind particles around the planet. The interaction between the solar wind and Earth's magnetic field creates a region called the magnetosphere, which is the volume of space around Earth where Earth's magnetic field dominates over the magnetic field of the solar wind. The magnetosphere is shaped somewhat like a teardrop, with a blunt nose facing the sun and a long tail extending away from the sun. The boundary between the magnetosphere and the solar wind is called the magnetopause, and it is located at a distance of about 10 Earth radii on the sunward side. On the night side, the magnetosphere stretches out into a long tail that extends hundreds of Earth radii into space. Most of the solar wind flows around the magnetosphere, like water flowing around a rock in a stream. But some particles do enter the magnetosphere, particularly at the poles, where the magnetic field lines are open and connect to interplanetary space. These particles can spiral along the field lines and enter the upper atmosphere, where they collide with atoms and molecules, causing them to emit light. This is the process that creates auroras. Auroras are most commonly seen at high latitudes near the magnetic poles because that is where the magnetic field lines guide particles into the atmosphere. The colors of auroras depend on which type of atom or molecule is involved and at what altitude the collisions occur. Oxygen at high altitudes produces red light. Oxygen at lower altitudes produces green light, the most common aurora color. Nitrogen produces blue and purple light. The patterns and movements of auroras, the curtains and arcs and rays, are determined by the structure of the magnetic field and the flow of particles along field lines. During strong geomagnetic storms, when the solar wind is particularly intense, perhaps due to a coronal mass ejection, the magnetosphere is compressed, and more particles enter the atmosphere. This can cause auroras to be visible at much lower latitudes than usual, sometimes as far south as the tropics in extreme cases. These intense storms can also cause other effects, such as fluctuations in power grids, disruptions to radio communications, and damage to satellites. The solar wind does not stop at Earth. It continues outward, past the orbits of Mars, Jupiter, Saturn, Uranus, and Neptune, past the Kuiper Belt, past the orbit of Pluto, and on into the outer solar system. All along the way, it is gradually slowing down as it pushes against the thin gas of the interstellar medium, the matter that exists in the space between stars. At some distance, the solar wind slows from supersonic to subsonic speeds, crossing a boundary called the termination shock. Beyond the termination shock is the heliosheath, a region where the solar wind is still moving outward but is no longer supersonic. And beyond the heliosheath is the heliopause, the boundary where the pressure of the solar wind is finally balanced by the pressure of the interstellar medium and the sun's influence ends. The solar wind is not uniform. It has two main components, the slow solar wind and the fast solar wind. The slow solar wind has speeds of about 300 to 500 kilometers per second. The fast solar wind has speeds of about 700 to 800 kilometers per second. Both types exist simultaneously, and the type that Earth encounters depends on the structure of the sun's magnetic field at any given time. The slow solar wind originates from regions near the sun's equator, particularly from areas where the magnetic field is complex and constantly changing. The fast solar wind originates from coronal holes, which are regions of open magnetic field lines near the sun's poles. These are areas where the magnetic field does not loop back to the sun, but instead extends out into space, allowing particles to stream away freely. At Earth's distance from the sun, the solar wind has a density of about 5 particles per cubic centimeter. For comparison, Earth's atmosphere at sea level has a density of about 2.5 times 10 to the 19th particles per cubic centimeter. So the solar wind, even though it is moving at hundreds of kilometers per second, is extraordinarily tenuous. It is, for all practical purposes, a near vacuum with a few fast-moving particles embedded in it. Despite its low density, the solar wind carries the sun's magnetic field with it. This is because the solar wind consists of charged particles, and charged particles interact with magnetic fields. As the solar wind streams outward, it drags magnetic field lines with it. The combination of the sun's rotation and the outward motion of the solar wind causes these magnetic field lines to take on a spiral shape called the Parker spiral, named after physicist Eugene Parker, who first predicted the existence of the solar wind in the 1950s. Parker's prediction of the solar wind was initially met with skepticism. At the time, the prevailing view was that space was empty between planets. But Parker's theoretical work showed that the sun's hot corona should be constantly expanding outward, filling the solar system with a tenuous stream of particles. He was correct. In 1962, the Mariner 2 spacecraft flew past Venus and confirmed the existence of the solar wind. Parker lived to see his prediction vindicated many times over and even saw a NASA mission, the Parker Solar Probe, named in his honor. The solar wind extends outward from the sun in all directions, creating a bubble-like region called the heliosphere. The heliosphere is the volume of space where the solar wind is still moving outward faster than the speed of sound in the surrounding interstellar medium. At some distance from the sun, the solar wind slows down as it encounters the thin gas that fills the space between stars. This transition region is called the termination shock. The termination shock is located at about 75 to 90 astronomical units from the sun, depending on the direction. An astronomical unit, remember, is the distance from Earth to the sun, so the termination shock is 75 to 90 times farther from the sun than Earth is. This is well beyond the orbits of all the planets. Neptune, the farthest planet, orbits at about 30 astronomical units. The termination shock is another 2 to 3 times farther out. Beyond the termination shock lies the heliosheath, a region where the solar wind has slowed to subsonic speeds but is still flowing outward. Beyond the heliosheath lies the heliopause, which is the boundary where the solar wind's pressure is balanced by the pressure of the interstellar medium. Beyond the heliopause, you are in interstellar space. You have left the sun's sphere of influence and entered the realm between stars. Only 5 spacecraft have traveled far enough to cross the heliopause and enter interstellar space. Voyager 1 crossed in 2012 at a distance of about 121 astronomical units. Voyager 2 crossed in 2018 at about 119 astronomical units. These spacecraft are still sending back data, providing the first direct measurements of the conditions in interstellar space. The other 3 spacecraft expected to reach interstellar space eventually are Pioneer 10, Pioneer 11, and New Horizons, though contact has been lost with the Pioneers, and New Horizons is still in the heliosphere as of 2025. The heliopause is not stationary. It expands and contracts depending on the strength of the solar wind, which varies with the solar cycle. During periods of high solar activity, the solar wind is stronger and the heliopause is pushed farther out. During periods of low solar activity, the pressure decreases and the heliopause contracts inward. The shape is also not perfectly spherical. The heliosphere is more elongated in the direction the Sun is moving through the galaxy, somewhat like a comet's tail, though this tail structure is not fully understood. Inside the heliosphere, we are protected from a significant fraction of cosmic rays. Cosmic rays are high-energy particles, mostly protons, originating from outside the solar system, perhaps from supernovae or other energetic, astrophysical processes. They travel through space at nearly the speed of light and can be harmful to living tissue and to electronic systems. The Sun's magnetic field, carried by the solar wind, acts as a shield, deflecting many cosmic rays before they reach the inner solar system. This shielding effect is called solar modulation. The level of cosmic ray shielding varies with the solar cycle. During solar maximum, when solar activity is high and the magnetic field is strong, cosmic ray intensity at Earth is lower. During solar minimum, when the Sun is quieter, cosmic ray intensity is higher. The difference is significant enough that astronauts planning long-duration missions, such as to Mars, must take into account the timing of their mission relative to the solar cycle to minimize radiation exposure. The solar wind is not always calm. Occasionally, the Sun ejects large bursts of plasma called coronal mass ejections, or CMEs. These events can occur when magnetic field lines in the Sun's corona become twisted and suddenly release energy, hurling billions of tons of plasma into space at speeds of several hundred to over 1,000 kilometers per second. If a CME is directed toward Earth and reaches us, it can compress Earth's magnetosphere and cause geomagnetic storms, which can disrupt satellites, communications, and even power grids. The most famous example of a geomagnetic storm caused by a CME occurred in 1859, an event now known as the Carrington event. On September 1st and 2nd of that year, British astronomer Richard Carrington observed a massive solar flare on the Sun. About 18 hours later, a CME associated with the flare reached Earth. The resulting geomagnetic storm was so intense that auroras were visible as far south as the Caribbean, and telegraph systems across Europe and North America experienced widespread disruptions, with some telegraph operators reporting shocks and sparks. If an event of that magnitude occurred, today the consequences could be far more severe given our reliance on electrical grids and satellite technology. However, such extreme events are rare, occurring perhaps once every few centuries. Most geomagnetic storms are much milder and cause little more than beautiful auroras at high latitudes. The solar wind is a reminder that the Sun is not a distant, isolated object. Its influence extends throughout the solar system, creating an environment that shapes the conditions on every planet. Without the solar wind and the heliosphere, Earth would be bombarded by much higher levels of cosmic radiation. The solar wind is part of the system that makes Earth habitable. It is part of the Sun's continuous presence, extending outward, creating a zone of relative calm in the much harsher environment of interstellar space. There is something comforting in knowing that we are inside this protective bubble, carried along with the Sun on its journey through the galaxy, shielded from much of what lies beyond. The heliosphere is vast, extending billions of miles into space, yet it is finite, and within it we exist, along with all the planets and moons and everything else in the solar system, moving together through the galaxy at 500,000 miles per hour, yet feeling none of it because we are all moving together. The Sun does not rotate as a solid body. This is possible because the Sun is not solid. It is plasma, and different parts of the plasma can rotate at different rates. This phenomenon is called differential rotation, and it has been known since the early 17th century when Christoph Scheiner observed that sunspots at different latitudes on the Sun moved at different speeds. At the Sun's equator, a point on the surface completes one full rotation in about 25 days. This is the rotation period measured relative to distant stars, called the sidereal rotation period. Measured from Earth, which is itself orbiting the Sun, the apparent rotation period is slightly longer, about 27 days, because Earth has moved in its orbit during that time. This 27-day period is called the synodic rotation period. As you move toward higher latitudes, away from the equator, the rotation period increases. At about 30 degrees latitude, north or south, the rotation period is about 26 to 27 days. At 60 degrees, it is about 30 days. At the poles, the rotation period is about 34 to 35 days. So a point at the equator completes a rotation in 25 days, while a point at the pole takes 35 days. The equator is rotating about 40% faster than the poles. This differential rotation has profound effects on the Sun's magnetic field. Magnetic field lines in the Sun are rooted in the plasma and are carried along as the plasma rotates. Because the equator rotates faster than the poles, magnetic field lines get stretched and twisted over time. Imagine a rubber band wrapped around a ball. If you spin the equator faster than the poles, the rubber band will start to wind up and become twisted. The same thing happens with the Sun's magnetic field. Over time, this twisting and stretching causes the magnetic field to become more complex and tangled. Regions of strong magnetic field can push through the surface, forming what we observe as sunspots and active regions. Eventually, after about 11 years, the magnetic field becomes so tangled that it reverses polarity. The north magnetic pole becomes the south magnetic pole, and vice versa. Then the cycle begins again. After two such reversals, spanning about 22 years, the magnetic field returns to its original configuration. This 22-year period is called the Hale cycle. The reason for differential rotation is related to the Sun's internal structure. In the radiative zone, below the convection zone, the Sun rotates more or less as a solid body. The rotation rate in the radiative zone does not vary significantly with latitude. But in the convection zone, convection currents and the Coriolis effect caused by rotation create complex flow patterns that lead to differential rotation. The boundary between the radiative zone and the convection zone, where the rotation changes from solid body rotation to differential rotation, is called the tachocline. The tachocline is a thin layer, only a few % of the Sun's radius in thickness, but it is thought to play a crucial role in generating the Sun's magnetic field. The combination of differential rotation in the convection zone and the shear between the solid body rotation of the radiative zone and the differential rotation of the convection zone creates conditions favorable for amplifying magnetic fields. This process is part of what is called the solar dynamo. The solar dynamo is the mechanism by which the Sun generates and maintains its magnetic field. It involves the interaction between the Sun's rotation, convection, and existing magnetic fields. Small, seed magnetic fields are amplified by the differential rotation, which stretches and winds up field lines, converting kinetic energy of rotation into magnetic energy. Convection then lifts and distorts these magnetic fields, causing them to emerge through the surface. The details are complex and not fully understood, but the general principle is that the sun's rotation and convection work together to create a self-sustaining magnetic dynamo. Differential rotation is not unique to the sun. It has been observed on other stars and on the gas giant planets Jupiter and Saturn. Jupiter's equator rotates faster than its poles, just like the sun, though the difference is less pronounced. Saturn also exhibits differential rotation, with the equatorial regions rotating faster than the polar regions. These planets are also not solid, and the same principles that cause differential rotation in the sun also apply to them. On Earth, differential rotation does not occur in the solid crust, but it can occur in the atmosphere. Winds at different latitudes on Earth move at different speeds due to the Coriolis effect and the distribution of solar heating. The jet streams in Earth's atmosphere are an example of differential rotation. They are fast-moving currents of air that flow from west to east at middle latitudes, driven by the temperature difference between the equator and the poles and influenced by Earth's rotation. The fact that the sun rotates at all tells us something about its origin. When the cloud of gas and dust that formed the sun collapsed under gravity, it had some initial rotation, probably just a slow tumble. As the cloud collapsed and became smaller, conservation of angular momentum caused it to spin faster, just like a figure skater spins faster when they pull their arms in. By the time the sun reached its current size and began fusion, it was rotating much faster than the original cloud. Over time, the sun has been gradually slowing down, transferring angular momentum to the solar wind and to the planets through gravitational interactions, but it still retains enough angular momentum to complete a rotation in about a month. The sun's rotation can be observed in several ways. The most direct method is to track sunspots as they move across the sun's face. Sunspots are dark regions on the photosphere caused by strong magnetic fields, and they typically last for days or weeks. By watching a sunspot appear on the eastern limb of the sun, move across the solar disk, and disappear over the western limb, and then reappear on the eastern limb about 27 days later, astronomers can measure the sun's rotation period. Another method is to use spectroscopy. When the sun rotates, one side is moving toward us and the other side is moving away. Light from the side moving toward us is blue-shifted, meaning its wavelength is shortened, while light from the side moving away is red-shifted, meaning its wavelength is lengthened. By measuring these shifts across the sun's disk, astronomers can determine the rotation rate at different latitudes. A third method is helioseismology, which studies waves that propagate through the sun's interior. These waves cause small oscillations on the sun's surface, which can be detected by measuring tiny Doppler shifts in the light from different parts of the sun. By analyzing these oscillations, scientists can infer the rotation rate not just at the surface, but also deep within the sun's interior. This has revealed that the radiative zone rotates nearly uniformly, while the convection zone exhibits the differential rotation we observe at the surface. The sun's rotation is steady and predictable. It does not speed up or slow down noticeably over human timescales. The rotation period has been roughly constant for millions of years. There may be very slow changes over billions of years as the sun gradually loses angular momentum, but on any timescale relevant to human civilization, the sun's rotation is a fixed, reliable characteristic of our star. This constancy, this predictability, is part of what makes the sun such a stable platform for a planetary system. If the sun's rotation were erratic, its magnetic field would be erratic, and the solar wind and space weather would be far more unpredictable. As it is, the sun rotates smoothly, its magnetic field evolves on an 11-year cycle, and conditions in the solar system, while variable, are broadly stable over long periods. This stability is part of the foundation on which life on Earth has been built. The Sun's magnetic field undergoes a regular cycle of change, known as the solar cycle, with a period of approximately 11 years. This cycle is evident in the number of sunspots that appear on the Sun's surface, the frequency of solar flares and coronal mass ejections, and the overall level of solar activity. At the beginning of a cycle, sunspots are relatively rare. As the cycle progresses, the number of sunspots increases, reaching a maximum around the middle of the cycle, and then decreases again as the cycle ends. At the same time, the Sun's magnetic field reverses polarity. The north magnetic pole becomes the south magnetic pole, and vice versa. After two 11-year cycles, or about 22 years, the magnetic field returns to its original configuration, having reversed and then reversed again. This 22-year period is called the Hale cycle, but most discussion of solar activity focuses on the 11-year sunspot cycle, since that is the most obvious pattern in observations. Sunspots are regions on the photosphere where the magnetic field is particularly strong, several thousand times stronger than Earth's magnetic field. These strong magnetic fields inhibit convection, preventing hot plasma from rising to the surface in those regions. As a result, sunspots are cooler than the surrounding photosphere, with temperatures around 7,000 degrees Fahrenheit compared to 10,000 degrees in the rest of the photosphere. This lower temperature makes them appear darker. Despite being darker and cooler, sunspots are still extremely hot by any terrestrial standard. A sunspot would glow brightly if it were isolated in space. It only appears dark in contrast to the even brighter surrounding photosphere. Sunspots range in size from small spots a few hundred miles across to large, complex groups spanning tens of thousands of miles, larger than the diameter of Earth. Sunspots usually appear in pairs or groups with opposite magnetic polarities. One spot in a pair will have a north magnetic polarity, and the other will have a south magnetic polarity, like the two poles of a bar magnet. These pairs are aligned roughly east to west, and are the visible signs of magnetic field lines that have emerged from below the surface. The magnetic field loops up out of one sunspot, arcs through the corona, and returns down into the Sun at the other sunspot in the pair. The number of sunspots varies over the 11-year solar cycle. At solar minimum, there may be days or even weeks when no sunspots are visible on the Sun. At solar maximum, there may be dozens of sunspots and sunspot groups visible simultaneously. The transition from minimum to maximum and back to minimum is gradual, taking place over several years. The latitude at which sunspots appear also changes over the cycle. At the beginning of a new cycle, sunspots tend to appear at latitudes around 30 to 40 degrees north and south of the equator. As the cycle progresses, new sunspots appear at progressively lower latitudes, closer to the equator. By the end of the cycle, sunspots are appearing at latitudes around 5 to 10 degrees. Then a new cycle begins, and sunspots start appearing again at higher latitudes. This pattern was first described by astronomer Richard Carrington in the 19th century and is often shown in what is called a butterfly diagram because the pattern of sunspot latitudes over time resembles the wings of a butterfly. The solar cycle has been observed and recorded for centuries. The first clear identification of the 11-year cycle was made by Heinrich Schwabe, a German astronomer, in 1843, after he spent 17 years counting sunspots. His discovery was the culmination of patient observation, demonstrating that the Sun's appearance was not constant but followed a regular pattern of change. Since then, astronomers have continued to track sunspots and solar activity, assigning a number to each solar cycle. The first cycle to be numbered was Solar Cycle 1, which began in 1755. As of January 2026, we are in Solar Cycle 25, which began in December 2019. Solar maximum for Cycle 25 is expected to occur around 2025 or 2026, meaning we are currently near or at the peak of activity. The strength of each solar cycle varies. Some cycles have a high number of sunspots at maximum with intense solar activity. Other cycles are weaker, with fewer sunspots and less activity. There is no clear pattern to these variations. Cycle 24, which preceded the current cycle, was one of the weakest on record, with a low maximum sunspot number. Cycle 25 appears to be of moderate strength, neither particularly weak nor particularly strong. Occasionally, the Sun has entered periods of prolonged low activity with very few sunspots for many decades. The most famous such period is the Maunder Minimum, which lasted from about 1645 to 1715. During the Maunder Minimum, sunspots were extremely rare and some solar cycles appeared to be absent entirely. This period coincided with a time of cooler temperatures in Europe known as the Little Ice Age, though the causal relationship between low solar activity and cooler climate is still debated. Solar activity affects the space environment in the solar system. During periods of high activity, solar flares and coronal mass ejections are more frequent. Solar flares are sudden, intense bursts of radiation from the Sun, while coronal mass ejections are huge eruptions of plasma that can travel through space and reach Earth. When a coronal mass ejection impacts Earth's magnetosphere, it can cause geomagnetic storms, which create auroras and can disrupt satellites, communications, and power grids. Auroras, also known as the Northern Lights in the Northern Hemisphere and the Southern Lights in the Southern Hemisphere, are caused by charged particles from the solar wind and coronal mass ejections entering Earth's upper atmosphere and colliding with atoms and molecules there. These collisions excite the atoms, causing them to emit light. The colors depend on which type of atom is involved. Oxygen produces green and red light, while nitrogen produces blue and purple light. Auroras are most commonly seen at high latitudes near the magnetic poles, because that is where the Earth's magnetic field channels the charged particles down into the atmosphere. During strong geomagnetic storms, auroras can be visible at much lower latitudes than usual. During the Carrington event in 1859, auroras were reported as far south as the Caribbean and Hawaii. In more recent times, strong storms in March 1989 and October 2003 produced auroras visible across much of the northern United States and Europe. The solar cycle also affects the level of cosmic ray shielding provided by the Sun's magnetic field. During solar maximum, when the Sun's magnetic field is strong and complex, cosmic rays are more effectively deflected and fewer reach the inner solar system. During solar minimum, the shielding is weaker and more cosmic rays penetrate to Earth and other planets. This variation is significant for space missions, as cosmic rays pose a radiation hazard to astronauts, and missions can be planned to minimize exposure by launching during solar maximum when shielding is strongest. Understanding the solar cycle is important for space weather forecasting. Just as meteorologists forecast weather on Earth, space weather forecasters monitor the Sun and issue warnings when solar flares or coronal mass ejections are detected. This allows satellite operators, power grid managers, and others to take precautions to protect their systems. Space weather forecasting has become increasingly important as our technological infrastructure has become more dependent on satellites and electronic systems vulnerable to solar disturbances. The solar cycle is driven by the solar dynamo, the process by which the sun generates its magnetic field. The details of the dynamo are complex and not fully understood, but it involves the interaction between the sun's differential rotation, convection, and magnetic fields over the course of about 11 years. These processes wind up the magnetic field, amplify it, cause it to emerge as sunspots, and eventually reverse its polarity, after which the cycle begins again. Despite the regular period of the solar cycle, predicting the exact timing and strength of the next maximum or minimum is difficult. The cycle is not perfectly periodic. Some cycles are shorter than 11 years, some are longer, and the strength varies from cycle to cycle. Scientists use a combination of observations and models to make predictions, but there is always uncertainty. This unpredictability is a reminder that the sun, while stable overall, has internal dynamics that are not fully deterministic or easy to forecast. Nevertheless, the existence of the solar cycle is itself a sign of order and regularity. For at least the past few centuries, and likely for much longer, the sun has followed this pattern of increasing and decreasing activity. The cycle is not chaotic or random. It is a structured process driven by the laws of physics and the sun's internal dynamics. And even though we cannot predict every detail, we know that the sun will continue to go through this cycle, producing periods of high and low activity in a rhythm that has persisted for as long as we have been able to observe it. The sun's total energy output, also called its luminosity, is about 384.6 septillion watts. That is 3.846 times 10 to the 26th power in scientific notation. This number is so large that it is difficult to comprehend in any intuitive way. To put it in perspective, the sun produces more energy in 1 second than all of human civilization has produced in all of history. This energy comes from nuclear fusion in the core, as we have discussed, where about 4 million tons of matter are converted into energy every second, according to Einstein's equation. The energy is released as photons, which slowly make their way outward through the sun's interior over the course of about 170,000 years, eventually escaping from the photosphere and traveling into space. The sun radiates this energy uniformly in all directions, spreading it out over an ever-expanding sphere as the photons travel outward. Earth is located about 93 million miles from the sun, so by the time the sun's energy reaches Earth, it has spread out over a sphere with a surface area of about 2.8 times 10 to the 23rd square meters. Earth, with a cross-sectional area of about 1.3 times 10 to the 14 square meters, intercepts only a tiny fraction of the sun's total output, about 450 trillionths of a percent. Even this tiny fraction is an enormous amount of energy. The total solar energy reaching Earth is about 174 petawatts, which is 1.74 times 10 to the 17 watts. For comparison, the total power consumption of all of a human civilization is currently around 18 terawatts, or about 1.8 times 10 to the 13 watts. This means Earth receives about 10,000 times more energy from the sun every second than humanity currently uses. If we could capture and use even a small fraction of the solar energy reaching Earth, it could provide more than enough power for all of human needs. The amount of solar energy reaching a square meter of surface at the top of Earth's atmosphere is called the solar constant. It is approximately 1,367 watts per square meter. This is the amount of power that would be available from the sun for solar panels mounted on a satellite, assuming perfect efficiency. At Earth's surface, the amount is lower due to absorption and scattering by the atmosphere, typically around 1,000 watts per square meter on a clear day when the sun is directly overhead. The solar constant is not perfectly constant, despite its name. It varies by about 0.1% over the course of the 11-year solar cycle, being slightly higher during solar maximum and slightly lower during solar minimum. There are also small variations over longer timescales related to changes in the sun's structure and activity. However, these variations are tiny compared to the total output. To a very good approximation, the sun's luminosity has been stable for billions of years. This stability is one of the sun's most important characteristics from the perspective of life on Earth. If the sun's output varied significantly over short timescales, Earth's climate would be highly unstable, swinging between extreme heat and cold. Life would have difficulty adapting to such rapid changes. But because the sun's output is so stable, Earth's climate has remained within a relatively narrow range for most of its history, allowing life to evolve and thrive. The sun's luminosity has not been constant over its entire history, however. Stars gradually increase in luminosity as they age. When the sun first entered the main sequence phase, about 4.6 billion years ago, it was about 30% less luminous than it is today. Over the billions of years since, as helium has accumulated in the core and the core has become slightly denser and hotter to maintain the same pressure, the sun's luminosity has gradually increased. It is currently about 1% more luminous every 100 million years. This gradual increase in luminosity is slow enough that it has not caused catastrophic changes on Earth, but it has had effects. Early in Earth's history, when the sun was cooler, Earth should have been colder, possibly frozen. Yet we have evidence of liquid water on Earth from nearly 4 billion years ago, suggesting that Earth was somehow warmer than expected. This is known as the faint young sun paradox. The most likely explanation is that Earth's early atmosphere contained higher concentrations of greenhouse gases, which trapped heat and kept the surface warm despite the weaker sunlight. Over the next few billion years, the sun will continue to gradually increase in luminosity. In about 1 billion years, it will be about 10% more luminous than it is today. This additional heating will likely make Earth too hot to support life as we know it. The oceans may begin to evaporate, and Earth could enter a runaway greenhouse effect similar to what has happened on Venus. But this is far in the future, and it is a reminder that even the sun's remarkable stability is not eternal. Nothing in the universe is truly static. Everything changes, just very slowly on the timescales we are most familiar with. The sun's spectrum, the distribution of its energy across different wavelengths, is roughly that of a black body at 5,772 degrees Kelvin, the temperature of the photosphere. A black body is an idealized object that emits radiation based solely on its temperature, and the sun approximates this quite well. About 50% of the sun's energy is emitted as infrared light, which we feel as heat. About 40% is emitted as visible light, which we see. About 10% is emitted as ultraviolet light, which we cannot see but which can cause sunburn and other effects. The peak of the sun's spectrum is in the green part of the visible spectrum, which is why the sun would appear greenish-white if we could see it from space without atmospheric scattering. On Earth, the atmosphere scatters shorter wavelengths more than longer wavelengths, which is why the sky is blue and why the sun often appears yellowish or even reddish near the horizon. But the sun itself is white, emitting light across the entire visible spectrum. The energy that leaves the sun as light and makes its way to Earth has a journey of 8 minutes and 20 seconds, as we have noted, after which it can be absorbed by the land, the oceans, the atmosphere, or by plants through photosynthesis. Nearly all the energy that drives Earth's climate, weather, ocean currents, and ecosystems ultimately comes from the sun. The only significant exceptions are geothermal energy from Earth's interior and tidal energy from the moon's gravitational pull. Photosynthesis, the process by which plants convert sunlight into chemical energy, is the foundation of nearly all life on Earth. Plants capture solar energy and use it to convert carbon dioxide and water into glucose and oxygen. Herbivores eat plants, carnivores eat herbivores, and so on up the food chain. All of this is powered by sunlight. Without the sun's steady output, Earth would be dark, cold, and lifeless. The fact that the sun produces so much energy so reliably, day after day, year after year, for billions of years, is something we often take for granted. It is easy to forget that this constancy is not a given. It is the result of physical processes in the sun's interior that maintain a delicate balance between gravity and pressure, between energy production and energy loss. The sun is not struggling to maintain this balance. It does so naturally as a consequence of its structure and composition. But the fact that it does so at all, and that it does so for billions of years, is what makes the sun the perfect star for a planet like Earth. The sun is currently a main sequence star. This term comes from a graph called the Hertzsprung-Russell diagram, developed independently by Danish astronomer Einar Hertzsprung and American astronomer Henry Norris Russell in the early 20th century. This diagram plots the luminosity of stars, how bright they are, against their surface temperature or spectral type. When astronomers began plotting stars on this diagram, they discovered that stars were not randomly distributed. Instead, most stars fell along a diagonal band running from the upper left, where hot, bright stars reside, to the lower right, where cool, dim stars reside. This diagonal band is called the main sequence. Stars on the main sequence are all doing the same thing, fusing hydrogen into helium in their cores. This is the primary energy source during the longest phase of a star's life. The main sequence is not a line in space or a physical structure. It is a region on a diagram, a classification that tells us what the star is doing internally. Main sequence stars are in the most stable, longest-lasting phase of stellar evolution. Before reaching the main sequence, stars are protostars, contracting under gravity and heating up. After leaving the main sequence, stars enter various end-of-life phases, which can be relatively brief compared to the main sequence lifetime. The Sun has been on the main sequence for about 4.6 billion years. It formed from a collapsing cloud of gas and dust, spent about 50 million years as a protostar, and then ignited fusion in its core, entering the main sequence. Since then, it has been steadily fusing hydrogen into helium, maintaining the same basic structure and producing roughly the same luminosity, though it has gradually become slightly brighter over time. The Sun will remain on the main sequence for another 5 billion years or so, give or take a billion years. The exact timing depends on the details of how the Sun's structure evolves, which in turn depends on complex physics that is not fully understood. But the broad outlines are clear. The Sun is about halfway through its main sequence life. It is middle-aged. It has already lived for roughly as long as it has left to live. This is a reassuring time frame. It means that the Sun is stable and will remain so for a period of time much longer than life has existed on Earth, much longer than complex organisms have existed, much longer than humans have existed. The total lifetime of a star on the main sequence depends on its mass. This might seem counterintuitive at first. You might think that a more massive star, having more fuel, would live longer. But the opposite is true. More massive stars have more hydrogen, yes, but they also burn through it much, much faster. This is because a more massive star must generate more energy to support itself against gravitational collapse. The more massive the star, the higher the core temperature and pressure, and the faster fusion occurs. The relationship between mass and main sequence lifetime is quite steep. A star with 10 times the mass of the Sun might only live for 20 million years on the main sequence, which is 500 times shorter than the Sun's 10 billion year lifetime. A star with half the mass of the Sun might live for 80 billion years, which is 8 times longer than the Sun. A star with 1/10 the mass of the Sun might live for 10 trillion years, which is 1,000 times longer than the Sun and longer than the current age of the universe. These vastly different lifetimes have profound implications for the evolution of stars and galaxies. Massive stars live fast and die young. They spend only a few million years on the main sequence before exhausting their hydrogen, evolving into supergiants, and eventually exploding as supernovae. All of this happens so quickly that massive stars are relatively rare in the galaxy at any given time, not because they are rare in absolute terms, but because they do not last long. Most of the massive stars that have ever formed have already died. Low-mass stars, on the other hand, live for extraordinarily long times. A red dwarf, a star with about 1/10 the mass of the Sun, will remain on the main sequence for trillions of years. No red dwarf has ever left the main sequence because the universe is not old enough. The universe is only about 13.8 billion years old. Red dwarfs can live for hundreds of billions or even trillions of years, so every red dwarf that has ever formed is still shining, still fusing hydrogen in its core. They will continue to do so for the vast majority of the universe's future history. The Sun, with its one solar mass by definition, sits comfortably in the middle of this range. It has a main sequence lifetime of about 10 billion years, which is neither particularly short nor particularly long on cosmic timescales. This lifetime is, however, quite long on biological timescales. 10 billion years is more than twice the age of the Earth and more than twice the amount of time life has existed on Earth. It is long enough for complex life to evolve, for intelligence to arise, for civilizations to develop. If the Sun were a more massive star, it would have left the main sequence much sooner. Perhaps life would have had time to evolve on Earth, but perhaps not. The first life on Earth appeared about 3.8 billion years ago, only about 800 million years after Earth formed. If the Sun were twice as massive, it might have only lived for 2 billion years on the main sequence, which is not much time for life to get started, and certainly not enough time for complex life to evolve. Conversely, if the Sun were a less massive star, it would live longer, but it would also be dimmer and cooler, which could make it harder for planets to maintain habitable conditions. The fact that Sun-like stars are common in the galaxy is encouraging for the search for extraterrestrial life. There are billions of stars in the Milky Way with masses similar to the Sun, and many of them likely have planets. If some of those planets are in the habitable zone, the region where liquid water can exist, and if those planets have been stable for billions of years, then the conditions necessary for life to emerge and evolve may exist in many places. We do not know if life has actually arisen elsewhere, but the conditions that allowed it to arise on Earth are probably not unique. The Sun's stability as a main sequence star is maintained by a balance between the inward pull of gravity and the outward pressure from fusion in the core. This balance is called hydrostatic equilibrium. If fusion were to increase, producing more energy, the core would heat up and expand, reducing the density and slowing the fusion rate back down. If fusion were to decrease, the core would cool and contract, increasing the density and speeding up the fusion rate. This self-regulating mechanism keeps the Sun in a stable state. Hydrostatic equilibrium is not a static condition. The Sun is constantly producing energy, radiating it into space, and converting mass into energy. But the balance between gravity and pressure remains essentially constant, and the Sun's overall structure remains stable. This stability is not precarious. It is robust. The Sun has maintained this equilibrium for 4.6 billion years, and it will continue to maintain it for billions more, barring some catastrophic external event, which is extraordinarily unlikely. This stability is what has allowed Earth to exist as a habitable planet for billions of years. If the Sun were unstable, if its luminosity varied significantly over short timescales, Earth's climate would be chaotic. Temperatures would swing between extremes, making it difficult or impossible for life to adapt. But because the Sun is stable, Earth's climate has remained within a relatively narrow range, at least narrow enough that liquid water has existed on the surface continuously for most of Earth's history. This climatic stability is one of the prerequisites for the evolution of complex life. The Sun's luminosity has not been perfectly constant, however. It has gradually increased over the Sun's lifetime. When the Sun first entered the main sequence, it was about 70% as luminous as it is today. Over the past 4.6 billion years, it has gradually brightened, and it is currently about 1% more luminous every 100 million years. This gradual increase is a consequence of the accumulation of helium in the core. Helium is denser than hydrogen, so as helium accumulates, the core becomes slightly more compressed. To maintain hydrostatic equilibrium, the core heats up and the fusion rate increases, causing the Sun to become more luminous. This gradual brightening has had effects on Earth's climate. Early in Earth's history, when the Sun was cooler, Earth should have been colder, possibly frozen. Yet we have evidence of liquid water on Earth from almost 4 billion years ago, suggesting that Earth was somehow warmer than expected. This is called the faint young sun paradox. The most likely explanation is that Earth's early atmosphere contained much higher concentrations of greenhouse gases, such as carbon dioxide and methane, which trapped heat and kept the surface warm despite the weaker sunlight. Over time, as the Sun has brightened, the concentration of greenhouse gases in the atmosphere has decreased, either through natural processes or through the influence of life, maintaining a relatively stable climate. In the future, the Sun will continue to brighten. In about 1 billion years, the Sun will be about 10% more luminous than it is today. This might not sound like much, but it will be enough to make Earth uncomfortably hot. The additional heat will accelerate the weathering of rocks, which removes carbon dioxide from the atmosphere. Eventually, the carbon dioxide concentration may drop so low that plants can no longer photosynthesize. Without plants, the food chain collapses, and complex life on Earth will come to an end. The oceans may begin to evaporate, leading to a runaway greenhouse effect. Earth will become uninhabitable, not because the Sun has died, but simply because it has become too bright. But this is still 1 billion years away. For context, 1 billion years ago, the most complex life on Earth was simple multicellular organisms. Animals had not yet evolved. Plants had not yet colonized the land. 1 billion years is an almost unimaginable span of time on biological and geological scales. Over this period, continents will move, mountain ranges will rise and erode, entire evolutionary lineages will appear and disappear. The Earth that exists 1 billion years from now, even before the Sun becomes too bright, will be unrecognizable compared to the Earth of today. Eventually, in about 5 billion years, the Sun will run low on hydrogen in its core. Hydrogen will still be present in the outer layers, but the core will be mostly helium, which does not fuse at the current core temperature and pressure. When this happens, fusion in the core will cease. Without fusion to provide outward pressure, the core will begin to contract under gravity. As it contracts, it will heat up, because gravitational potential energy is being converted into thermal energy. Eventually, the temperature in a shell around the core will become high enough to fuse hydrogen. This is called shell burning. The energy produced by shell burning is greater than the energy that was produced by core burning. This additional energy heats the outer layers of the Sun, causing them to expand. The Sun's radius will increase dramatically, perhaps to 100 times its current size. As the Sun expands, its surface cools because the same amount of energy is being spread over a much larger area. The cooler surface temperature gives the Sun a reddish color. The Sun has become a red giant. As a red giant, the Sun will be enormous, extending perhaps as far as the orbit of Mars or even beyond. Mercury will almost certainly be engulfed and vaporized. Venus will probably be engulfed as well. The fate of Earth is uncertain. The Sun's expansion will cause it to lose mass, which will weaken its gravitational pull on the planets, causing their orbits to move outward. Earth might move far enough to avoid being engulfed, or it might not. But even if Earth is not physically swallowed by the Sun, the increased radiation will make it uninhabitable long before that point. The red giant phase is not stable. The Sun's outer layers, distended and loosely bound, will pulsate and may be gently ejected into space, forming a planetary nebula. Meanwhile, the helium core will continue to contract and heat up. Eventually, the temperature will become high enough for helium fusion to ignite. Helium fuses into carbon and oxygen through a process called the triple alpha process. When helium fusion begins, it does so suddenly in an event called the helium flash. For a brief period, the helium fusion rate is enormous, but the core quickly adjusts and the fusion settles into a stable rate. The helium burning phase lasts for about 100 million years, much shorter than the hydrogen burning main sequence phase. During this time, the Sun will be very luminous, though not as extended as during the initial red giant expansion. Eventually, the helium in the core will be exhausted, leaving a core of carbon and oxygen. The Sun will attempt to contract further, but it is not massive enough to ignite carbon fusion. Carbon fusion requires temperatures and pressures that only stars with masses of at least about 1.4 solar masses can achieve. The Sun, with one solar mass, falls short. Without fusion to support it, the core will contract until electron degeneracy pressure stops it. This is a quantum mechanical effect that arises because electrons, being fermions, cannot occupy the same quantum state. As the core contracts and electrons are squeezed into a smaller and smaller volume, eventually they run out of available quantum states, and further compression becomes extraordinarily difficult. The core, now supported by electron degeneracy pressure rather than thermal pressure, becomes a white dwarf. A white dwarf is incredibly dense. The Sun's core, with a mass of about half the current mass of the Sun, will be compressed into an object about the size of Earth. The density will be about 1 million times greater than the density of water. A teaspoon of white dwarf material would weigh several tons. The white dwarf will be very hot initially, perhaps 100,000 degrees at the surface, but it will no longer be producing energy through fusion. It will simply be radiating away its stored thermal energy, gradually cooling over billions or even trillions of years. This is the ultimate fate of the Sun. It will not explode as a supernova. It will not collapse into a black hole. It will simply end its life as a cooling ember, a white dwarf slowly fading into darkness. But again, this is far in the future, billions of years away. For the foreseeable future, on any time scale relevant to human existence, or even to the existence of life on Earth, the Sun will remain as it is, a stable main sequence star, shining steadily, providing the light and warmth that makes life possible. The total lifetime of a star on the main sequence depends on its mass. More massive stars have more fuel, but they also burn through it much faster because they must generate more energy to support their greater mass against gravitational collapse. As a result, massive stars have shorter lifetimes. A star with 10 times the mass of the Sun might only live for 20 million years on the main sequence. A star with half the mass of the Sun might live for 80 billion years, far longer than the current age of the universe. The Sun, with its one solar mass by definition, has a main sequence lifetime of about 10 billion years. This is long enough that the Sun is currently only about halfway through its main sequence life. It is a middle-aged star, neither young nor old. It has already lived for 4.6 billion years and has about 5 billion years remaining before it exhausts the hydrogen in its core and begins to evolve off the main sequence. This long lifetime is one of the reasons the Sun has been such a good host for life. Life on Earth has had billions of years to evolve, from simple, single-celled organisms to the complex ecosystems we see today. If the Sun were a more massive star, it would have left the main sequence much sooner, possibly before life had time to evolve into anything more than simple forms. If it were a less massive star, it might have lived longer, but it would also be dimmer and cooler, potentially making it harder for planets to maintain habitable conditions. Stars of similar mass to the Sun are common in the galaxy. There are billions of Sun-like stars in the Milky Way, and many of them likely have planets orbiting around them. Some of those planets are probably within the habitable zone, where liquid water can exist. The question of whether life exists on those planets is one of the great unanswered questions of science, but the fact that Sun-like stars are so common suggests that the conditions necessary for life are probably not rare. The Sun's stability as a main sequence star is maintained by a balance between the inward pull of gravity and the outward pressure from fusion in the core. If fusion were to increase, producing more energy, the core would heat up and expand, reducing the density and slowing the fusion rate. If fusion were to decrease, the core would cool and contract, increasing the density and speeding up the fusion rate. This self-regulating mechanism keeps the Sun in a stable state, which is called hydrostatic equilibrium. Hydrostatic equilibrium is what allows the Sun to remain stable for billions of years without collapsing under its own gravity or exploding from the energy produced by fusion. It is a kind of balance, a steady state where the forces are equal and opposite. This equilibrium is not static. The Sun is constantly producing energy, radiating it into space, and converting mass into energy. But the balance between gravity and pressure remains, and the Sun's overall structure remains stable. Eventually, in about 5 billion years, the Sun will run low on hydrogen in its core. Hydrogen will still be present in the outer layers, but the core will be mostly helium, which does not fuse at the temperatures and pressures present there. When this happens, fusion in the core will cease. Without fusion to provide outward pressure, the core will begin to contract under gravity. As it contracts, it will heat up. This increasing temperature will eventually ignite hydrogen fusion in a shell around the helium core. At this point, the Sun will leave the main sequence and begin to evolve into what is called a red giant. The shell fusion will produce more energy than the core fusion did when the Sun was on the main sequence, causing the outer layers of the Sun to expand. The Sun's radius will increase dramatically, growing to perhaps 100 times its current size. It will become cooler at the surface, giving it a reddish color, hence the term red giant. The increased radius and cooler temperature will make the Sun much more luminous than it is now, perhaps a few thousand times more luminous. As a red giant, the Sun will engulf the inner planets. Mercury will almost certainly be consumed. Venus probably will be as well. The fate of Earth is less certain. The Sun's expansion will cause it to lose mass, which will weaken its gravitational pull on the planets, causing their orbits to move outward. Earth might move far enough to escape being engulfed, or it might not. Even if Earth is not consumed, the increased heat from the Sun will make it uninhabitable long before that point. After the red giant phase, the Sun's helium core will eventually become hot enough to ignite helium fusion. Helium fuses into carbon and oxygen through a process called the triple alpha process. This helium fusion phase will last for only about 100 million years, much shorter than the hydrogen fusion phase. During this time, the Sun will be even more luminous, though not as large as during the initial red giant expansion. Eventually, the Sun will exhaust its helium as well. Without fusion to support it, the core will contract again, but this time it will not become hot enough to fuse carbon. Stars need a mass of at least about 1.4 solar masses to ignite carbon fusion. The Sun is not quite massive enough. Instead, the core will contract until electron degeneracy pressure stops it. This pressure comes from a quantum mechanical effect that prevents electrons from occupying the same state. The core will become a dense ball of carbon and oxygen about the size of Earth, supported by electron degeneracy pressure. This object is called a white dwarf. Meanwhile, the outer layers of the Sun will be gently ejected into space, forming what is called a planetary nebula. Despite the name, a planetary nebula has nothing to do with planets. It is simply a shell of gas expanding away from the white dwarf. The name comes from early telescopic observations where these nebulae appeared round and somewhat planet-like through small telescopes. The planetary nebula will expand and fade over tens of thousands of years, dispersing into the interstellar medium. The white dwarf will remain, slowly cooling over billions or even trillions of years, eventually becoming a cold, dark ember known as a black dwarf. This is the ultimate fate of the Sun, but it is far in the future. For the next 5 billion years, the Sun will remain on the main sequence, steadily fusing hydrogen into helium, producing the light and warmth that Earth depends on. There is no immediate danger, no crisis on the horizon. The Sun is stable. It will remain stable for a time so long that it is beyond meaningful human comprehension. This stability, this reliability, is perhaps the Sun's most remarkable feature. It is not the largest star, it is not the brightest star, it is not the most massive or the hottest or the longest lived, but it is stable. It has been stable for 4.6 billion years, and it will remain stable for billions more. This stability is what has allowed Earth to exist as a habitable planet, with liquid water, a stable atmosphere, and an environment where life could emerge and evolve. Without the Sun's stability, none of this would be possible. The Sun is a relatively ordinary star, but from our perspective, it is the most important star in the universe. It is the source of light, warmth, and energy for Earth. It determines the rhythm of our days and seasons. It shapes our climate and our weather. It is the reason that Earth is a habitable world rather than a frozen rock drifting through space. And yet, for all its importance to us, the The Sun is just one star among hundreds of billions in the Milky Way galaxy. If you could travel far enough from Earth, the Sun would become just another point of light, indistinguishable from countless others. It would lose its special status, becoming just another star in the vast tapestry of the galaxy. But from here, from this particular planet, orbiting this particular star, the Sun is everything. It is the reason the sky is bright during the day. It is the reason plants grow and food exists and the seasons change. It is the reason that warmth exists at all on a planet that would otherwise be frozen. Without the Sun, Earth would be a dark, cold, dead world, with a surface temperature near absolute zero and no liquid water, no atmosphere, no life. This dependence on the Sun is absolute. There is no substitute. No other source of energy could provide the consistent, long-term power that the Sun provides for free every single day. No technology we currently have or can foresee could replace the Sun's role in Earth's environment. We are tied to the Sun, as we have been since Earth first formed, and as we will be for as long as Earth remains habitable. But this dependence is not a vulnerability. It is simply the nature of being a planet. Planets do not generate their own heat and light in the way stars do. They rely on their star for that. This is how planetary systems work. A star provides energy, and planets, if they are at the right distance, can become warm enough for liquid water and life. This is not a flaw, it is the design of the universe at this scale. The Sun will continue to shine for billions of years. It will continue to provide light and warmth. It will continue to follow its regular cycles and patterns. And Earth will continue to orbit, receiving that light and warmth, maintaining the conditions that allow life to persist. There is a rhythm here, a constancy, a reliability that is almost comforting. The Sun will rise tomorrow. It will rise the day after that. It has risen every day for billions of years. It will rise every day for billions more. Of course, on human timescales, the Sun's behavior is not perfectly predictable. Solar flares, coronal mass ejections, and other forms of solar activity can affect Earth in various ways, from creating beautiful auroras to disrupting satellites and power grids. But these are minor perturbations in the grand scheme. The Sun's fundamental nature, its luminosity, its temperature, its size, all of these remain stable over timescales far longer than human lifetimes, longer than human civilizations, longer than human existence as a species. This is perhaps the most comforting thing about the Sun. It does not change in ways that matter to us. It does not suddenly become brighter or dimmer. It does not move closer or farther away. It does not flicker or dim. It simply continues day after day, year after year, providing exactly the amount of energy that Earth needs to maintain the delicate balance that supports life. There is a kind of peace in that knowledge. The universe is vast and complex and often unpredictable, but the Sun is reliable. It is a constant in a changing world. It was here before us, and it will be here long after we are gone. It will continue its journey through the galaxy, carrying the solar system with it, providing light and warmth to Earth and the other planets, unchanged in its essential nature for billions of years to come. And, in that continuity, in that steady, patient, unending process, there is something deeply reassuring. The Sun is not just a ball of hot plasma. It is a symbol of constancy, of reliability, of the kinds of patterns and rhythms that the universe creates and sustains over unimaginable spans of time. It is a reminder that some things, at least, are stable and enduring, even as everything else changes around them. We've spent time together with the Sun, moving through its layers, exploring its processes, understanding a bit more about this star that sits at the center of our solar system. It is not necessary to remember every number or every detail. What matters is the overall sense of what the Sun is. A massive, stable, luminous sphere of plasma that has been quietly doing its work for billions of years and will continue for billions more. The light that reaches you now, if you're reading this during the day, or the warmth on your skin if you're outside, began as fusion reactions in the Sun's core 170,000 years ago. It bounced through the radiative zone, was carried upward by convection, escaped from the photosphere, crossed 93 million miles of empty space in 8 minutes, and now it is here. That same process is happening right now, as it has happened every moment since the Sun ignited, and as it will happen every moment for the rest of the Sun's long life. There is something calming in knowing that this process is reliable, that the Sun will be there tomorrow and every day after, that it has created the conditions for life on Earth and will maintain those conditions for as long as we could possibly need. We did not earn this. We do not control it. It is simply given freely and constantly by the physics of a star in its prime. The Sun is not mysterious in the sense of being unknowable. We understand, to a remarkable degree, how it works, why it shines, what it is made of, and what its future holds. But there is still something profound about a star, any star, and especially this one. It is a reminder of the scale of the universe, of the vastness of time, of the processes that created everything we know. You can rest now if you'd like. The Sun will continue. It does not need your attention or your concern. It simply is, as it has always been, as it will always be for longer than we can truly comprehend. If you found this exploration calming, if it helped you rest or think or simply be present for a while, consider liking this video and subscribing to the channel. There are more journeys like this one, more explorations of the universe's quiet wonders, more opportunities to learn and relax at the same time. Thank you for spending this time with the Sun. May it continue to shine on you steadily and gently every day.